Example number 6.8. This figure is given. Arm PQ of the rectangular conductor is moved from x is equal to 0 outward. So the rod is moving in this particular direction. Okay, here we take x is equal to 0 and then x increases as you go from left to right. Okay, now we are going up to x is equal to b, and up to this point, up to x is equal to b here, okay, there is a magnetic field. Then outside this means if you are moving from b to 2b, this distance is how much? 2 times b. Then here in this region there is no magnetic field. Okay, consider the situation when the arm PQ is pulled outward from x is equal to 0 to x is equal to 2b and is then moved back to x is equal to 0 to again, means again you are coming back to x is equal to 0. So what happens? You are moving in this direction. First you are going in this and then moving in this particular direction. Okay. Obtain expression for the flux, the induced EMF, the force necessary to pull the arm and the power dissipated as joule heat. Sketch the variation of these quantities with distance. Okay. Now see, first of all, flux is B into A. Okay, that is area multiplied by the magnetic field. Okay, rather B dot A, but area and magnetic field are in same direction, therefore B A cos 0. Now flux is BLX because length of the rod multiplied by the distance x. Okay, length of the rod multiplied by the distance x, that will give you length into breadth and that will give you area. Okay, so that is why we write BLX, that is nothing but the flux phi b, that is BLX. Okay, and this flux will be BLX up to this distance equal to b, means as you move from this point to this point, the x increases and therefore the flux also increases. Okay, so at this point, that is at point B, the flux becomes BLB. Now try to understand, when you go this side, then this flux associated is going to remain constant. Flux is not going to change. That is equal to BLB only. If you come back, then also till this point the flux is going to remain BLB. Okay. Now when you cross this point and go this side, then flux decreases. So initially flux increases. Try to understand, when you go from this point to this point, flux increases. Then from this to this, it remains constant. When you come from this point to this point, again it remains constant. And when you cross this point and come back to the original point, x is equal to 0, the flux reduces. So the graph of this will be initially flux increases up to x is equal to b. Then it remains constant up to 2b, then again you come to b and then it reduces. So first nature of the graph will be like this, that is explained here. Okay, K to L, flux increases, L to M, M to L again. Okay, the flux remains constant, and L to K, the flux reduces. Okay, then induced EMF is d phi by dt, it is minus BLV. Okay, according to Faraday's law. Okay, so here up to B point, that is at this particular point, okay, where the magnetic field is there, up to the point where the magnetic field is there, this point, the flux changes and electromotive force is produced, and that electromotive force will be BLV. Okay, so up to this point the electromagnetic force will be BLV with negative sign. Now when you go out, no magnetic field, so electromotive force is 0. Then from this point again you come to this x is equal to b, again no magnetic field, again flux, the electric motive force is 0. Then you go this side. Okay, then again it will be BLV, but the velocity in opposite direction, so it will be positive BLV. Okay, so the graph goes like this. Okay, from the point of initiation to point L, the electromotive force is BLV. Then 0, no electromotive force, so 0 it is shown. Again coming back, it is 0, then direction changes, then this value BLV is positive. Okay, now next, force. Okay, current can be given by BLV upon R, that can be understood. Its magnitude is BLV upon R, that is voltage upon resistance. Now we talk about the force. Force is IL cross B, IL be sin 90. Okay, so force is I, instead of I we write BLV upon R, so this value of force becomes B square L square V upon R. And try to understand, up to point B there is magnetic field, so force will be there, that is B square L square V upon R. And if you go out of the B, that is from this point, if you go out of the B means, if you go out of X is equal to B, there is no magnetic field. Here there is no magnetic field, so the value of force will be equal to 0. Okay, so again you will have the graph similar to that of electromotive force. Okay, the magnitude of this force will be minus B square L square V upon R initially, then no force, then again, okay, the positive value will be there. Power is, as you know, power is I square R BLV upon R whole square, that will give you B square L square V square upon R square, and this multiply by R, so it becomes B square L square. Okay, this is very easy. I is BLV upon R whole square into R. If you simplify, then this value you will get. Power is always positive, so that is going to remain positive only. Okay, but when you go from X is equal to 0 to X is equal to small b, okay, what will happen? This power will be increasing. Okay, or rather it will be B square L square V square upon R, and then it will become 0. Okay, and then again you come back, it is 0, then again it will be positive. Okay, now example number 6.9. Two concentric circular coils, one of smaller radius R1 and the other larger radius R2, okay, such that R1 is smaller than R2, are placed coaxially with the centers coinciding. Obtain the mutual inductance of the arrangement. Now smaller coil is kept here and outer is the bigger coil. The radii are R1 and R2 respectively. This radius is R1, and as you know, R1 is very much smaller than R2. Now let us say that current is flowing in the second coil, and that is equal to I2. Okay, now the flux associated with this is phi is equal to B dot A, BA cos 0. Area of this coil will be pi R1 square into magnetic field of second, that is P2. Okay, so pi R1 square and magnetic field of second B2 is mu 0 I2 upon 2 times the radius. So mu 0 I2 upon 2 R2 it will become, or we can say magnetic field of second is mu 0 I2 upon 2 times R2. Okay, so that value if you substitute here instead of B2 and you keep pi R1 square, then this will be mu 0 pi R1 square I2 upon 2 R2. Okay, so here this phi 1 can be here this M12, rather we can say this constant values mu 0 pi R1 square upon 2 R2 is mutual inductance M12. Okay, rather we can say flux of first divided by current of second, flux of first coil and the current of second coil, that will give you mutual inductance of the system M12. So if you take phi 1 upon I2, then also you will get mu 0 pi R1 square upon 2 R2. Okay, and as you know, reciprocity theorem M12 is M21, so both the values are same. Okay, so these values we got that of mutual inductance of the arrangement. Now very important one, obtain the expression for the magnetic energy stored in the solenoid in terms of magnetic field B, area A and length L of the solenoid. How does this magnetic energy compare with the electrostatic energy of the capacitor? As you know, the energy stored in the solenoid is given by 1 half Li square. Okay, and as you know, B is equal to mu 0 Ni. So make I as a subject of formula, you will get B upon mu 0 N. Okay, so this value of I, if you substitute here instead of this I, okay, it becomes B upon mu 0 N whole square. And if you simplify this, then it will become 1 by 2. As you know, L is given by the self inductance, okay, and self inductance is mu 0 n square Al. So instead of L we are writing this mu 0 n square Al, and this value you keep as it is. Okay, so what is the what difference which we made? Instead of L we are writing mu 0 n square Al, and this you are keeping as it is. Okay, so if you simplify this and rearrange them, then you will get 1 upon 2 mu 0 B square into Al, which is the energy stored with the solenoid. Okay, now the magnetic energy per unit volume, that is energy divided by volume is area into length. So whatever value which we got here UB, that you divide by A into L, so you will get B square upon 2 mu 0, okay, which is similar to the equation which we have got in the electrostatic, 1 by 2 epsilon 0 E square. Okay, so this is your magnetic energy per unit volume, this is electrical energy per unit volume associated with capacitor, and this is associated with the solenoid. Okay, now 6.11, Kamala pedals stationary bicycle. The pedals of the bicycle are attached to 100 tons coil of area 0.1 meter square. The coil rotates half revolution per second. So its frequency is given, and the place a uniform magnetic field of 0.01 Tesla perpendicular to the axis of rotation of the coil. What is the maximum voltage? Now maximum voltage is NBA omega, and omega is 2 pi nu. So just you have to place the values here. N is given, magnetic field is given, area is given, 2 pi, and nu is half rotation per second. So 0.5, if you simplify, then maximum voltage you will get. Here our illustration part of this chapter is getting over. Thank you very much. Calculate this 2-3 times and practice.